Well, Sean, clearly no questions left.
No,
that's
thanks.
it. Done, everyone.
I would be insulted if there were questions.
I expect there are lots of questions, in fact, and there are microphones I expect going around right now. Whilst those microphones go around, put your hands up for your questions, of course, and we'll get a microphone to you. Wait till the microphone gets to you, and we'll come to you guys upstairs as well, although we can't actually see you because of the intense electromagnetic field in our direction from up there. Before I come to you guys, though, if you can pick a question from each side, maybe we can start with there. Yeah. I'm going to ask a question, because I think I get to, right? Now, I've read a description of the book that you've written. I believe you've written a book.
I've written a book.
I've read a description about how the Large Hadron Collider was built. It was a long project, decades, political shenanigans. You write about skullduggery, a bit of naughty behavior from scientists. Tell us a bit about the naughty behavior and the skullduggery that involved in building this monumental machine.
The naughty behavior, I'm not sure if I have a good LHC-based story. I mean, in the history of particle physics, there are many fun stories about naughty behavior. There's at least, it's just the truth, there's at least one Nobel Prize winner who went up to a competitor's experiment and urinated on it. I'm not going to, you can Google it. Okay.
It wasn't a $9 billion experiment.
Well, you know, he knew that it was a symbolic gesture. He was not trying to. But the problem is, as far as my book and the stories inside it are concerned, is that the stories don't come out until much later. So the LHC is all, you know, there was political intrigue because things were happening like Europe was reuniting. Okay, one of the major monetary contributors to CERN is Germany, and in the early 1990s, they had other things to worry about than the search for the Higgs boson. They were trying to absorb East Germany and so forth. So there was a lot of, you know, patting of the back and so forth. Here in Britain, David Waldegrave was the science minister, and he very famously was talking to the particle physicists, and after talking to the particle physicists for a certain amount of time, he said, "Guys, I have no idea what you're talking about. Come back tomorrow and give me a one-page long description of the Higgs boson. If you can do it, I will give you a bottle of champagne and vote for the LHC. If you can't, sorry." David Smith was the winner of the bottle of champagne, and he gave the analogy of two people moving through an empty room. Me, he didn't use me, I can use me, and Margaret Thatcher. And we imagine that if the room is empty, we both move at the same speed. But if the room is full of British people, suddenly Margaret Thatcher is a celebrity and I'm not, so Margaret Thatcher is slowed down moving through the room, whereas I can walk at the same speed. So the people in the party play the role of the Higgs field filling space. That is a story that I tell in the book. It's not nearly as good as the old school stories. Like Carlo Rubbia, you know, he had his experiment ready, the previous Large Hadron, not as large, but large collider at CERN. He had his experiment, it was almost ready. It was this gold-plated, wonderful experiment. He had competitors who were sort of doing a smaller experiment. It was cheaper, it was not supposed to be as good, but they were ready first. So CERN tried to turn on the machine and he flooded the tunnel. So they couldn't turn on the machine until his experiment was ready, and he later won the Nobel Prize for discovering the W boson.
And there you go. Let's go for a question from over here. So how about you at the front there? And then get ready with a question here as well. So.
Hi, is this on?
Just keep talking.
Just keep talking.
Okay.
Oh goodness.
Okay, first of all, love the book. Great stuff. I was wondering if you could just talk a little bit about the idea that Higgs is a scalar field, and does the discovery of the Higgs make other hypothesized scalar fields like the inflaton field more likely?
That's a man who knows his physics.
Someone has been cheating, learning about particle physics before coming to the talk. So it turns out that, of course, there are many different fields that we saw on the plot. You know, here are just some fields that we are imagining. One way of talking about the fields is how many different components they have. Because, you know, sometimes I mention the electromagnetic field. Other times I mention just the electric field or the magnetic field. The electric field is something that is not just a value at every point in space. It's a little arrow at every point in space. It has a magnitude and a direction. Likewise, the magnetic field has a magnitude in a different direction in principle. But back in the 19th century, people figured out, Faraday played a big role in this, how to marry together the electric field and the magnetic field to make one thing called the electromagnetic field. So there are different categories of fields. There's the fermions, the bosons, etc. There was, remember, the flow chart that you memorized earlier. The Higgs boson is all by itself up there. Why is that? Well, one reason is because it is all by itself. It is only one field. It's one number. It is not a little arrow. It does not have multiple components. There's no antiparticle for the Higgs field. It's just the Higgs field, the Higgs boson field. So the label we attach to that is it is a scalar field. It's just a single number at every point in space. All of the other fields here have more than one thing going on. None of them are scalar fields. And so before we discovered it, there was this thought among physicists, this idea of the Higgs boson, a scalar field, plays this hugely important role in our theory of the Standard Model, but we've never found a scalar field. We found all these fermions and spin 1 bosons and spin 2 bosons and so forth. But now we have found the Higgs boson. So now all those snipers who didn't, who said, well, you haven't found a scalar field, well, now we can say, look, $9 billion later, we found it. That means that we're now even more licensed than we were before to invent new scalar fields. And we do that, especially cosmologists like myself love to invent new hypothetical scalar fields to get the universe going at early times, to be the dark matter, to give rise to new long-range forces, and so forth. So, but to be honest, and to answer your question, we weren't really shy about doing that before. So it makes it a little bit more legitimate, this scalar fieldology, because now we've actually found one. But, we're pretty shameless when it comes to that. So.
Thanks for your talk. It was wonderful. I realised that what I learned about physics at school was from 1935. So
it's a good year.
Good to be updated. I was wondering why, when the protons collide in the LHC, why would you expect to see a Higgs boson if it's outside of the photon?
That's a very, very good question. And I don't think I actually have a little diagram here, but let me wave my hands. That's a traditional response. So the proton is made of up quarks and down quarks held together by gluons. So you see on the left, we've indicated here, there are gluons that I didn't draw, but they're holding these things together. So when you smash two protons together, what's really going on is that inside the protons there are quarks and gluons, and it's not the proton that hits the proton, it's one of those quarks or gluons hits one of the other quarks or gluons. Sometimes the analogy is made that it's like smashing two wristwatches together and seeing what comes out and trying to figure out how wristwatches work by doing that. That is a bad analogy because there are no Higgs bosons inside the proton, which is exactly your question. So it's more like smashing two Timexes together and hoping a Rolex is spontaneously assembled by doing that. Because what you're doing really is setting up vibrations in the fields. So two gluons or two quarks come together, they're both vibrations in fields, and because you've put so much energy into these protons, they're vibrating to beat the band. Okay, so they're vibrating with a huge amplitude. They come together, and it's like if you play the piano in one room, a piano in the room next to you will start humming in sympathy and resonance. So these vibrating fields start all the other fields around them vibrating along with them. And then quantum mechanics gives you a probability that all those vibrations will show up in your detector as certain specific kinds of fields. The more energy you have in those vibrations, the heavier the new particles you can produce really are. So E equals mc squared, right? So this is actually, the fact that particles can turn into other particles is something that only makes sense because the world is really made of fields. Back when it were just particles, before quantum field theory was invented, we didn't know how to describe the changes, the transformations of one kind of particle into another. Now we know that at every point in space, all of these fields are vibrating and they're all gently talking to each other. And only when they're vibrating like crazy in the LHC can you create something new and heavy like the Higgs boson. We're going to insist that the snappily dressed young man ask a question.
How about you?
When you were talking about dark matter, you said that there's way more matter in the universe than the standard you didn't account for. What do you mean by that?
Yeah, I mean, what do you mean? What do I mean? That's what I mean.
Does the standard model theory say that there can only be a finite amount of matter in the universe?
No, that's right. That's a very, very good question. So here's the simple-minded thing that we do is we look to see how much matter there is in the universe. You know, we count the number of stars and galaxies, and also there's invisible matter in between the galaxies, but if you look using X-ray telescopes, you can even see that invisible matter. And then we weigh the galaxies and the groups of galaxies, and we find that there's much more matter there than what we counted. You might, if you were a conservative, nose to the grindstone kind of scientist, say, well, maybe you just missed it. Maybe there's matter that you don't see, but it's still there, but it's still the standard model, right? I mean, that's obviously your first idea. However, we have independent ways of saying exactly how much standard model matter there is in the universe. And that's because the universe started 13.7 billion years ago with the Big Bang. We didn't talk about that, but everything was fit very tightly together in a hot, dense, smooth state. And as the universe expanded and cooled, it went through a set of phases where all the matter interacted with each other. It went through a phase where the universe was a nuclear reactor. It was turning protons and neutrons into helium and lithium and deuterium. It went through another phase where it went from being opaque to being transparent. And in every one of these phases, it leaves behind fingerprints. How much helium did you get from the early universe? What kind of shadows do you see from that moment when the universe became transparent? And all of these moments, all of these clues that were left behind depend on the amount of ordinary matter in the universe, the amount of quarks and leptons, the standard model of particle physics. And whether we either look at the universe today or look at the products from its phase as a nuclear reactor, or look at that moment when it became transparent, we get the same answer every time. There's this much ordinary matter. And it's only 1/5 of what we need to explain the gravitational field in galaxies and clusters. So the extra matter we need to explain gravity is not standard model matter, or all of those predictions from the early universe would have been false.
Sean, how long have scientists known that most of the universe isn't accountable for? And how does it make scientists feel when they realize that what they thought was a complete theory is actually very incomplete?
The thing about scientists is everything makes them feel awesome, right? I mean, if they had been right, they'd have been like, awesome, we're right. When they're wrong, they're like, awesome, there's new things to discover, right? But it crept up on us. The idea that there is dark matter goes back to the 1930s. Fritz Zwicky was a Swiss-American physicist who worked at Caltech. He weighed the Coma cluster of galaxies. This is a nearby cluster of galaxies. And he showed that there was a lot more matter than we could account for by ordinary means. But in the 1930s, we didn't know enough particle physics to say how much standard model matter there really was. In the 1970s, Vera Rubin, an astronomer, showed that galaxies, you'd expect that galaxies, you can see what they look like, right? And you can see there's a lot of matter in the center and less on the outskirts. So she measured it, and she found that actually there's more and more matter as you go further and further away from the galaxy. So that's dark matter also. But this idea, your question, that we know how much ordinary matter there is, as opposed to dark matter, it was put forward in the 70s, but no one believed it, because it was astronomers, not particle physicists. In the 80s, it got better, and by the time I was in grad school, late 80s, early 90s, all right-thinking cosmologists accepted that this was true.
And then it was discovered or measured in the 90s, and the Nobel Prize was given only a few years ago.
Yeah, so there's dark matter, and then there's dark energy, right? So the pie chart is about 4% of the universe is ordinary matter. So this wonderful thing, I'm celebrating our discovery of this stuff. 4% of the universe is this stuff. 23% or so of the universe is dark matter, and another 73% is this dark energy stuff, which isn't even made of particles. And by the mid-1990s, we knew that it couldn't all be simple. We knew that something complicated was going on, but we didn't know what. In 1998, two groups of astronomers showed that the universe is not only expanding, but accelerating. And the only way to explain that is dark energy, and everything snapped into place.
Okay. We'll leave dark energy there for now. Another question here from Kevin.
Sean, thank you very much. Fantastic talk. You should write a book.
I should write a book, I know.
Is it possible that the fundamental truths will remain unknowable? Because you point out there that it takes €9 billion, dollars, whatever, and 3,000 scientists to know these things. And so that seems a geometric increase in the number of people or resources that you require to know the truth. The special relativity is had by one person less than a century before. Is it possible that the truth is beyond our resource in terms of intellectual power and collaboration and or financial resource?
It is possible. It is possible that the sun will use up its nuclear fuel and life on Earth will cease because it becomes cold and dark. But these are long-term worries. There's plenty in physics that we don't know the answer to. So an implicit message here, which I didn't spell out very carefully, but I could, is that quantum field theory lets us define much better than ever before the regime of what we do understand, the boundary past which, all right, I understand everything going on in here, but there could be surprises beyond that boundary. And that boundary is, getting more expensive to cross, and the LHC is a reflection of that. On the other hand, but there's two things. One is we know that there's stuff beyond that boundary. Dark matter and dark energy, the Big Bang, ensure that there is stuff there. It may become harder to find, but it's there, and so we have to look. We don't know. And it could be a cornucopia. We could double the number of particles, in the next 5 years. And the other thing is, just because we understand quarks and leptons and the four forces of nature, doesn't mean we understand economics. It doesn't mean we understand neuroscience or how hurricanes work, or for that matter, how this table works, really. It's the difference between knowing how the knight moves on a chessboard and being a grandmaster chess player, right? We now know the rules of chess as in terms of the fundamental workings of our little corner of reality. We're not very good at playing the game of putting those underlying laws to work and explaining things like the origin of life or other interesting questions. So of all the possible things that I could spend time worrying about, running out of either interesting questions to ask or the resources to answer them is not in my top 100. Okay, we get here first.
Hello. Oh, hi. I'm a bit of a physics ignoramus, so mine's quite a basic question. But I get the impression that the LHC was something incredible and new. And I was just wondering, when they built it and they started to experiment, was there any chance that something absolutely disastrous and awful and unpredictable could happen, like the world would explode or Switzerland would explode? I just wondered how risky and mysterious it was.
It is actually a good question. People, for example, there are respectable scientific theories that if they had been right, along with Higgs bosons, the LHC would have been making small black holes. And you might worry that one of those black holes would get captured by the Earth, go down to the middle, eat up all of the Earth, and the Earth would collapse into the black hole. Okay. So number one, the same theories that predict those black holes also predict that they would evaporate in a tiny fraction of a second. So it's hard to take the prediction halfway. Number two, if they didn't evaporate and they did fall into the center of the Earth, you could calculate how long it would take for the Earth to be eaten up. It's hundreds of trillions of years, much longer than the current age of the universe. Number three, and most importantly, all the other things are just window dressing. Even though the LHC does things that we human beings have never done before, it doesn't do anything the universe doesn't do all the time. The Earth is bombarded by high-energy cosmic rays, which collide with particles in our atmosphere with much higher energies than we create at the LHC. So it's not an airtight argument, but you would certainly expect that if anything terrible had gone wrong, making black holes or new phases of matter that would change things in any dramatic way, it would have happened a long time ago because the universe has been doing this experiment for a long time. Having said that, physicists took all of the possibilities very, very carefully. They wrote many white papers going through the argument the best they could, and they decided there was no substantial risk. And just to put an exclamation point on it, if you go home tonight and you make pasta with tomato sauce, and you open the jar of the tomato sauce, is it possible that inside that jar there's been a pathogenic mutation which will release a virus and kill all life on Earth? it's possible. But you're going to open the jar anyway, even though you get just this tiny little benefit. We are always balancing terrible sounding but radically unlikely consequences off of our everyday needs. So as far as the LHC is concerned, the payoff was much larger than a nice bowl of spaghetti, so it wasn't a hard problem.
Wasn't there someone in America who tried to sue
There was.
the organizers to stop them from starting the whole thing in the first place?
Yes, there was a gentleman named Walter Wagner, who was a high school science teacher, who made his living, he used to be a high school science teacher, now he makes his living suing people. And he sued the LHC in the district court in Hawaii, saying that they had not prepared a respectable, responsible environmental impact statement of destroying the world, would be the environmental impact that he was worried about. And it was thrown out.
Fortunately. Right, our question up here.
Yes, thank you very much. I've really learnt something here, which is great, brilliant lecture. You've explained, obviously, that our universe is composed of, I would say various, but I guess it's got to be different fields. Mm-hmm. What I'm interested is, looking at the ideas of parallel universe and the multiverse, would you expect, therefore, that there might be slight variations in those fields, as well as the possibility of different fields? And has there been any evidence produced of any slight variations in fields, or indeed different fields?
Yeah, that's a very good question. So there are two things you need to tell me to construct the laws of physics. One is, what are the fields? And the other is, what are the numbers that characterize those fields and how they interact with each other? What is, for example, the strength of gravity? What is the mass of the electron, which is just a way of saying what is the way that the electron interacts with the Higgs boson? So the number of fields is a discrete number. It's not something that can change smoothly. It's an integer, okay? You can't go from 11 fields to 11.9 fields or something like that. But the parameters, the mass of the electron, for example, that you could imagine changing gradually over space or over time. It is possible that it does. It is possible there is a multiverse of the kind where far outside the part of the universe we can see, the constants of nature, the parameters of physics, take on very, very different values. Within our observable piece of the universe, we have looked. We've looked a lot. So, for example, your question about the density of ordinary matter, I said, well, you can test that using the fact that the early universe was a nuclear reactor. Another thing you can test is, was the mass of the proton and the neutron the same 1 minute after the Big Bang as it is now? Because if it were different, the nuclear reactions would have been different. Everything we've done is compatible with the idea that the constants of nature are constant. They have not changed. But maybe we just haven't looked carefully enough. That's definitely an ongoing project.
No one yet has asked about the Avengers, but it's just me. I don't know.
The Higgs
if
boson
you find something
is much more interesting.
You say that. But over here.
And cheaper.
And cheaper, probably cheaper. Imagine. Maybe that's the scientific advice for the next Hollywood film. Just fund the next generation particle collider. Go for it.
Really great lecture, thank you. I was wondering, what's the difference between the vibrations of fields and, say, the vibrations of superstrings?
That's a good question. So my computer ran out of electricity, so I hope you don't want any more pictures. There is this idea out there called string theory, and your question is actually quite subtle, so I kind of wish you hadn't asked it. But when we think about particles and fields, relationship between particles and fields, we say, well, what really exists are fields, and if you look closely at them, they resolve into particles. And when physicists invented string theory, what they said was, just sort of quasi out of the blue, they said, well, what if we replaced the particles with little vibrating strings? They were hoping to understand some features of the strong interactions of nuclear physics, but what instead they predicted was gravity. And so string theory today is still the leading candidate we have for a quantum theory of gravity. What we don't quite have is what you would call string field theory, the string theory analog of quantum field theory for particles. So If in particle physics we say what really exists are fields and they vibrate, you look at them and you see particles, there should be something called string fields. And when they vibrate, you should look at them and you should see strings. We're not really quite sure what a string field would be. It's part of the fact that we don't really know what string theory is, right? It's an idea. We make a lot of progress thinking about it, but just like Isaac Newton didn't understand action at a distance, we don't understand string theory, really. And it's all of its predictions so far are outside the realm of experimental testability, so we're not getting any help from the data either. So I will just leave you with, that's a really good question. Go to school, answer it, and you'll in your Nobel lecture, you'll footnote this. I was in the Royal Institution and heard this lecture. I'd be happy to be thanked.
We've only got a few minutes left, so what I might do is get a few questions, then you can give rapid answers. Now, if you can keep your questions really, really quick, we can actually get maybe Sean to answer all of them really quickly. Go for
The quick version of the question is, given the expansion of the universe, what does that mean for conservation of energy? Photons stretch, gravity stretches out, vacuum energy stays pretty constant.
Right. The answer is energy is not conserved.
Oh,
and
actually, that's really interesting.
But you said I had to give a short answer to all the questions.
No, carry on.
If you Google energy is not conserved, you'll find a blog post by me. The reason you thought energy should be conserved is because you're used to being in a world where the ground beneath you is not changing. In an expanding universe, it is, and energy is no longer conserved.
That's radical. Go.
Could you give us a sense of the amount of data and the amount of analysis that was needed for the physicists at CERN to convince themselves that those bumps on the graphs were really the Higgs boson and not
Really big amount of data. CERN is the biggest database in existence here on Earth. It's the fastest information transfer between centers. It's just petabytes of data, and we have only just scratched the surface. We're collecting not only the same amount of data every year, but every year we go, we're collecting as much data as we have every year before combined.
And they had to invent a completely new way of storing and analyzing data, which we're going to use one day as a successor to the web. I mean, they're geniuses up there.
Yeah.
So over here.
So they say that the gravity of the particle is the graviton. So why is it so hard for you guys to detect it? So they haven't proved it yet.
There is a particle called the graviton, according to theory. We've not detected it yet, just because gravity is a very weak force, and therefore gravitons individually don't interact in a noticeable way. They interact, but we don't notice.
Okay, we're coming up to the end, so I'm going to ask one more question about the Higgs boson. Now, there is, Sean, we all talk about the Higgs boson giving things mass. Now, you've made sure that that's not how you describe it in your book. But can we just talk about how much of something's mass the Higgs boson actually gives?
Sure.
It's not, this is a mistake that people make. People think particles, mass, Higgs boson. It turns out that's not quite the picture, is it?
It is certainly not the picture. What I'm being careful, hopefully I was careful throughout the talk, the Higgs field filling empty space gives mass to elementary particles. That is to say, W bosons, electrons, the up quark, the down quark. It doesn't give mass to protons and neutrons because they're not elementary particles. They're combinations of quarks and gluons and so forth. It turns out that the mass of a proton is much more than the mass of the quarks inside the proton. It's the energy holding them together that really gives the proton and neutron their mass. And most of your mass comes from protons and neutrons, not from electrons and quarks. So if around you someone turned off the Higgs field, that's not a good diet plan, okay? You're not going to lose a lot of weight by someone turning off the Higgs field. Instead, all of your atoms would disintegrate and you would cease to exist. So most of your mass comes from the strong interactions, not from the Higgs field, but the Higgs field does make you possible.
And just one final thing. What's the point of the Higgs boson? Can we find a use for it? And most importantly, can a superhero use it in some way?
Yes.
To do something in one of the Avengers movies?
No. No, in fact, in one of the chapters of my book, I try to be as honest as I can. Throughout the history of physics, fundamental physics, just pie in the sky, trying to understand the fundamental laws of nature has always paid off technologically, whether it's magnetism or quantum mechanics or superconductivity or whatever. But there we were always discovering phenomena that were always right in front of us, we just didn't know it. The Higgs boson is not right in front of us. You need that Large Hadron Collider to make it. And you're not going to carry around a portable version of the Large Hadron Collider. There are spin-offs from this kind of research. Computing power, the World Wide Web was invented at CERN as a spin-off, superconductivity technology, and so forth. So for every dollar that you put into building the LHC, the world economy gets many dollars back. But that's not why we do it. We don't do it for better technology. We don't do it for spin-offs. We don't do it for economic gain. We do it because we want to know the answer. We want to know how nature works. You have to spend billions of dollars to do it. And we've been lucky enough to live in an era where the answers have been coming quite frequently.
Okay, well, Sean, thank you very much. I don't need to encourage you to put your hands together. But also, just don't remember, Sean will be signing his book just outside. So, Sean, thank you very much indeed.